Hi, today we're going to be talking about acid and base theory. So, acids and bases are normally thought of as Bronsted-Lowry acids, and these are things you've likely seen before in general chemistry or in high school chemistry. So, Bronsted-Lowry acid is something that gives you a proton, an H+, or delivers an H+. And a base, a Bronsted-Lowry base, is something that has the ability to abstract or accept an H+. And so when we look at that, the quintessential acid is H+, and hydroxide, OH, is a good base. When those two react, they give you water. Now, Lewis acids and bases are slightly different than Bronsted-Lowry acids and bases, and Lewis defined his acids as the ability to accept a lone pair of electrons, and a base as something that donates a lone pair of electrons. So when you look at a kind of a Venn diagram, if you had Bronsted-Lowry acids and bases in this circle, actually the Lewis would completely surround that circle and include that circle. And so it's always important to, if you're trying to remember what is a Lewis acid, if you look at H+, a proton, is a Lewis acid, and it only has the ability to accept electrons. It has no more electrons to give. So it is completely spent. It is just a nucleus. There are no electrons, and so it needs to accept a lone pair of electrons. And if you know what an acid is, the base is simply the opposite. So it's important to recognize the similarities and the differences between pH and the pKa. So they are both log scales. And sometimes I have a hard time visualizing what a log scale is. And so a log scale is that it goes from 1 is a single block, 2 would be 10 blocks, and 3 would now be 100 blocks. So it goes up in there's a huge difference in the number of objects from 1 to 2 to 3. And I won't even draw 4, it's too many. So, and pH is a measure of the concentration of how much H+ is in water. And when H+ is in water, what you're really actually measuring is the hydronium ion. A key feature of pH is that it is a measurement of this in water. So that is your solvent for pH. It has to be water. pKa instead actually relates the ratio of protonated and deprotonated compounds in a given solution. So if we look at an equation for that, if you have any given compound and it's in the presence of some sort of solvent, that solvent can abstract the proton. It can act as a base and abstract the proton from that acid to give you this conjugate base here, and now the protonated solvent. So we often see this in the context of HA, where A is just a random thing that the proton is attached to. It is your acid. The HA is your acid. A- is the conjugate base of this acid. And we often think about these pKa in water as well, which is often, I think, why it gets confused with pH. And there are, of course, relationships, and we'll look at that later in class, the Henderson-Hasselbalch relationship. So what is pKa? And so if you, again, have this reaction where you have a proton being abstracted by solvent and giving you the conjugate base and now the conjugate acid, the protonated solvent, this is an equilibrium. And what the pKa is really telling you is what side this equilibrium lies on. And so in order to look at that, we have to put we can put products over reactants, and we can look at Ka as the equilibrium constant. Now, something to note is that because the solvent is so abundant, the concentration of the solvent is effectively constant. So we can simplify our equation to simply be the conjugate base plus the conjugate acid over the concentration of the starting material. So the pKa, once you add that extra little p to it, is the negative log of that. And sometimes it's hard to think about what this means in terms of kind of practical purposes. So the way to think about it is as this gets bigger, that is, as the as the acid gives more of its protons to the solvent. Another way of saying that is as the acid becomes stronger, then the pKa ends up getting smaller. That's the way that this ratio would work, because, again, it's a negative of this. And it's also important to recognize that these numbers can become negative. I also point out that we often simplify this solvent H plus as simply H plus, and you'll sometimes see that in the book, or you'll see me use this as well. But it's important to recognize, actually, that the solvent does dictate the pKa. So the pKa of a given compound is dependent on the solvent that it is in. But what you really need to look at, especially for this class, is the stability of this conjugate base. The stability of the conjugate base is really the one of the most important factors here, and that's what we're going to look at in the next video.